There we go. Okay, that is the join code. You can use the Q&A. It should bring you directly into quizzes whenever we have them. But we'll see, I guess. All right. So chapter 8 is gases. All right. So we're going to start off, obviously, from a biological perspective. Okay. Sure. You'll also get the codes again every time I come up. All right, so respiratory therapists treat a range of patients. They perform a variety of diagnostic tests. This includes things like measuring the breathing capacity, the concentration of oxygen, carbon dioxide in a patient's blood, as well as the blood pH. So you've all probably experienced this, I imagine. Have you ever had your respiratory testing how well you breathe? They give you a little gauge thing, breathe out. Yeah, okay. And so they're actually using fairly simple calculations in these because they actually work quite well. They're very robust, right? The same calculations an atmospheric scientist would also use, in case you're wondering. Okay? And those are the gases, chemistry gas equations. So we all live at the bottom of what you can consider a sea of gases. We call this sea of gases, this solution that we live at the bottom of, the atmosphere. The gases in the atmosphere include some of the main components are O2, which is 21% of the atmosphere. This is what is vital to us as animals, and plants also need this as well. Okay? There's actually part of the respiration cycle that plants use O2. Right. N2, this is 78% of the atmosphere. Not super useful for us, the animals, but very, very, very important for the bacteria, usually on the nodules of plants, to fix the nitrogen that they need. Okay. So what type of atmosphere can we call our atmosphere? It's a nitrogen atmosphere, isn't it? Yeah. Okay. Almost every sci-fi that ever says nitrogen atmosphere gets that wrong. That planet's poisonous to us because it's a nitrogen atmosphere. Okay. By the way, would it be okay for the O2 content to be very, very high in our atmosphere? Would we survive that? No, that would be very, very bad. Okay. Oxidation would happen very fast, and more than that, things would burn really easy. Okay. O3, this is the ozone. This is formed in the upper atmosphere through the interaction of the oxygen with high energy light, specifically the high energy ultraviolet light. This is actually what the ozone layer does for us. We call it the ozone layer or ozone shield. It's actually just the natural consequence of oxygen reacting due to the UV, the high energy UV. It absorbs that high energy UV, keeping it from coming down here, hitting us. If that UV did hit us, we would tan in about half a minute. We would burn within the minute, and within 10 minutes, we would likely die. Okay? And plants would also all be dead within about 20, 30 minutes of being outside. All right? The ozone layer actually almost was on the course to be depleted, and we would have disabled that protection, and we would have wiped out almost all life on the planet down to about a meter or so into the ocean. That was a true apocalypse. We did avoid that. The ozone layer is recovering, okay? Though there's some really nasty consequences, some bad policies that were put in place recently being the last 20 years, that are actually causing that to reverse a little bit. Not the policies you think, by the way. It's actually policies that were designed to destroy ozone-depleting chemicals that caused it to be made so that companies could turn in that they destroyed it and get paid for it. So there's this huge stockpile now of ozone-depleting chemicals that might be released and then deplete the ozone horrifically and cause a bunch of people to die. Anyways. Ooh, so glad I can give you nightmare fuel. It's not going to happen because nobody's that crazy. All right. Now, other gases, these include argon, CO2, carbon dioxide. You've heard a lot about carbon dioxide due to global warming, of course, and water vapor. By the way, does anybody know what the majority of global warming is actually caused by? Is it caused by carbon dioxide? No, that's about 1/3 of the effect. It's water. The majority of global warming is actually the water vapor. Okay? We just can't do anything about it, so we ignore it. Yeah. I mean, you live in Tennessee. You know we can't do anything about water vapor. It's all over the place here. Note that these are all trace gases. There's actually very little of them. You'll note that 99% of the atmosphere has already been accounted for in the oxygen and nitrogen. Okay? There's almost no other gases in the atmosphere if you're looking at bulk amounts. Yeah. The rest are in very low concentration. So let's talk about the kinetic molecular theory. Gases consist of small particles. With a gas, we can basically look at the molecules as being analogous to each other and just very small particles that are bouncing around really fast. Okay? They move rapidly in essentially straight lines. They have essentially no attractive or repulsive forces because they're moving so fast and so far apart that they don't really have time to attract or repel each other. Okay? Now, there are derivations and special cases that you might have to use if you go on to things like engineering school, right? But this is a 99% of the time, kinetic molecular theory is all you need, and it'll work great. They're very far apart, so they don't really have a lot of time to interact. They don't have a lot of ability to interact because, again, according to those molecules, as a perspective from those molecules, they're extremely far apart. They have very small volumes compared to the volume of the container they occupy. Remember when we're talking about atoms, they're extremely small. And so the volume of the container they occupy as a gas, that is going to be very, very large. This is actually why you can compress the gas so much. They have kinetic energies that are going to increase with an increase in temperature. The kinetic energy temperature relationship, does anybody remember that I gave you? So temperature is a measurement of randomized kinetic energy. So the higher your average kinetic energy in a system, the higher the temperature. Okay? So that's what temperature always was. All right, so let's talk about the properties that we need to describe a gas. We have the pressure. The pressure is going to be very analogous to concentrations for a gas. Okay? It is the force that's exerted by the gas on the walls of the container. We have the volume. This is going to be the space that's occupied by a gas. The space that's occupied by a gas ends up being basically whatever the size of the container you happen to be contained within, right? And so in the case of a non-sealed container like this, the gas we're currently dealing with is the whole planet. Okay? Okay. The temperature, this is going to be T, temperature. Everybody's good with temperature, right? Fantastic. And then we have the amount. Now the amount is typically measured in N. This is actually going to be the abbreviation, one-letter abbreviation for moles. Okay? So N, the amount of gas, typically measured in moles. I know M was taken. Remember, M is meters, right? Yeah. So by the time we figured out what moles are, M was taken. Okay. Now, again, this is the volume. This right here would have a volume right there, right? And typically we're going to measure that in liters. We might measure that in milliliters if we need something smaller. If we need something a little bit larger, we'd be meters cubed. Okay? You will see a lot of the atmospheric science is done in meters cubed. It's weird. It's a little difficult for you to compare to other numbers. They could have just done prefixes with liters, but they did not. Wasn't my choice. Sorry, guys. Okay. Now, if you keep everything else consistent, what would you expect the volume of, say, a balloon to be like? Would the volume of the balloon change if everything else doesn't change? No, the balloon stays the same, doesn't it? Okay, what happens then if you get your filled balloons, they look beautiful, you're going to take them to somebody, and so you exit a store, and it's a cold winter day. What happens to your balloons? They shrivel and shrink, don't they? And so you already know the relationship between temperature and the volume of gas, don't you? Okay? When temperature goes down, volume goes down, doesn't it? Okay? What about as the volume goes up? What about the temperature going up? What does that do? Yeah, if it warms, it expands back out, doesn't it? And that's why when you go back into buildings where it's warmer, it's going to expand back out, isn't it? Okay. So the temperature, as the temperature is decreased, the molecules are going to move slower overall. They're going to have less collisions in that container. Those collisions are actually what is propping up the walls of that container for a balloon. Okay? Those collisions are what we're experiencing when we're experiencing those pressure. Okay? Remember that when you're looking at the molecules versus the overall space, those molecules could condense down a lot. Right? They do not fill that space up very well. And so what we're actually experiencing when we're experiencing the volume of a gas or we're experiencing the pressure from a gas is we're experiencing those collisions, it running into you over and over. Okay? So as the temperature increases, we're going to experience more collisions, decreases, experience less collisions. Pressure. So pressure is actually the measure of the gas particle collisions with a side of its container. It's measured in units similar to millimeters of mercury, mmHg. That is the same unit as torr. Has anybody ever seen torr? No? Has anybody seen mmHg? Okay. Oh, wow. Anyways, mmHg was the original unit. It was literally a column of mercury being measured with a meter stick. So you literally measured, the mercury went up 3 millimeters. There you go. They stopped using mercury, and so they converted it to a torsion meter, and they called it torr. Okay? It's a digital meter now. And they relabeled it to torr, so why they relabeled it, honestly, I probably wouldn't have. I don't think anybody actually gets helped by that, but they did, and it is. Right? ATM, atmospheres, guess how much pressure that one is? It's the atmosphere pressure. So if you have 1 atmosphere pressure, you have the pressure of Earth's atmosphere at sea levels. Yeah. More or less. 2 atmospheres would be? 2 Earth's atmospheres worth of pressure, right? Okay. Pascals or kilopascals. This is a somewhat more used one that you see more in industry and stuff. Then we have pounds per square inch, or PSI. That's probably the one most of you have seen. Yeah. Okay. That's fair. So you may be wondering, because Earth doesn't look very much like a container. Does it look so much like a container to you? Yeah, it kind of is. Yeah, it's more like a cup, I guess. Yeah. But so we're actually on the bottom of one of the walls, right? On Earth. That's the crust, right? And what we're experiencing, we don't really feel it right now because it's happening all around us evenly. But we're experiencing the pressure from the gas pushing down on us from gravity. Okay? And so if you were to take the atmosphere above you in it's not really a column, it's more like a cone above you, you're experiencing the weight of that right now. Okay? Pushing down on you. It's not a whole lot of weight, but it is there. That is then deflecting and pushing sideways all around you. Okay? Now, because we experience that evenly across the entirety of us, we don't really feel it, do we? Kind of like when you have evenly applied pressure around your entire wrist, you end up kind of ignoring it after a while, don't you? You stop being able to feel it. So what ends up happening is if you have some of that pressure removed, does anybody know what happens? What if some of the pressure gets removed from one side? Anybody ever felt a suction? That's what suction is. Some of the pressure gets removed from one side and you start feeling the atmospheric pressure on the other. That's that force that's holding your hand on with the suction. Okay? Do you know how much pressure can be applied from suction on planet Earth right now? Up to 1 atmosphere. Do you know what conditions a spaceship's designed to handle? Anybody watch Futurama? Oh, that's sad. If you ever get a chance, very funny. It can handle between 1 and 0 atmospheres. All right. Do you know where you'd have to go to get more pressure than that? Down into water, right? Yeah. If you go down in the ocean, you can get more pressure. Okay, so let's talk about measuring pressure. This is a barometer. It's going to measure the pressure exerted by gases in the atmosphere. It indicates the atmospheric pressure as the height in millimeters of mercury in a column. This was the original way to measure this. So the atmosphere of Earth was 760 mmHg, which is 760 torr. Okay, that's what those were related with. This is what it actually looks like. You'd have a vacuum tube here. It essentially was like a test tube. And then you'd fill that with mercury. You'd then put that upside down in a mercury pan. The mercury in the pan would actually get pushed by the atmosphere, right? That would force the mercury up when it's higher pressure. And when it's lower pressure, the mercury is going to come down and lower in the tube. That making sense? They work actually very well. Unfortunately, mercury is problematic. So we do not do that anymore. Which is a little sad because mercury thermometers and mercury barometers worked really well for what they were. And were very, very stable and long-term. And yeah. But yeah, better that we don't have the mercury flying around everywhere. All right. So atmospheric pressure, it's going to be the pressure exerted by a column of air on the top of the atmosphere to the surface of Earth. It's going to decrease as altitude increases because you have less atmosphere above you to push down on you. It's at 1 atmosphere at sea level overall. Now, everybody's heard of like high pressure fronts, low pressure fronts. You've watched Weather Channel? Okay. That's what that's talking about, right? So at some points, the pressure can vary depending on the conditions around it. Specifically, it's usually a temperature condition that's causing that variance, okay? All right, so anybody ever heard like water boils faster when you're in the mountains? No? Yeah, it's true. Water does boil slightly faster when you're in the mountains. It actually boils at a slightly lower temperature. And that's the pressure difference. All right, so these are some different units and how they can be converted right there. Note that back when they did mercury, they actually would use inch, the inch scale on the mercury sometimes. I know, extra confusion, right? For the most part, we're only going to be using things like atmospheres, torrs, millimeters of mercury. These would be the more rare ones that we would use. Science isn't typically done in those anymore. Okay? Even though car tires are still done. All right. So the atmospheric pressure is again going to change with variations in weather. It's going to change in variations with altitude. So for example, on a hot, sunny day, your mercury column would rise, indicating a higher atmospheric pressure. And that's because, again, as you heat a gas, it's going to have more collisions. Those collisions are the pressure, right? And so we'll increase the pressure for our container. Our container happens to be the atmosphere around us. Okay. On a rainy day, the atmosphere exerts less pressure. This is going to cause the mercury column to fall, and that's that low pressure front that you've been hearing about, etc. Okay. Now, why would a low pressure meaning a high pressure front be an issue, by the way? Okay, when we had a vacuum on one side of things, what happened? Yeah, it moved things, right? It moved your hand. And so when we have a high pressure versus a low pressure front, gases from the high pressure front are going to move fairly rapidly into the low pressure front. Unfortunately, if a lot of gases move really rapidly, we sometimes call those things tornadoes if they go fast enough, or hurricanes if they're big enough, right?
Is that why people get headaches like before storms and stuff?
Yeah. Yeah. They can get slight variations in pressure, and our nasal cavity actually takes up this area right here. And so if you have slight differences in pressure, sometimes that nasal cavity doesn't change as fast, and it builds up a bit of pressure in your head. Okay, everybody ready for my question? I'm going to test whether you understood something. All right. So what is 475 mmHg as expressed in atmospheres? How would I convert that? It's a multiple choice, so you can actually ballpark it. So can it be 475 atmospheres? No. So how many mmHg was there for a atmosphere? 760, you got it. 760 mmHg. And so, well, our number is going to have to be something smaller than 1 atmosphere, isn't it? Okay, because we're not up to 760 mmHg, are we? Okay, and so that's going to end up being that 0.625 atmospheres, isn't it? Okay. By the way, what would this be? The 3.6 times 10 to the 5th? Yeah, it's if you mess up and multiply these things, you'd get a number like that. Okay, so let's check it out. Fantastic. Okay, so let's try another one. The pressure in a tire is 2 atmospheres. What is this pressure in mmHg? All right, make sure you got your answer in. I'm going to move forward. All right, and that is correct. Very good. Yeah, we just multiplied 760 by 2, right? Okay. Okay. So, the downward pressure on the Hg, the mercury, in the barometer is blank, the pressure of the atmosphere. Is it less than, same as, greater than? Okay. Go ahead and get your answer in. I'm missing quite a few people for some reason. There we go. Okay. And so that has to be the same as, right? So remember that mercury pan is exposed to the atmosphere. There's no containment that's going to keep those gases from moving around, right? So if you have open containers, they're going to equalize pressure all the time. Okay? All right. So, a water barometer is 13.6 times taller than a mercury barometer. So the DHG would be 13.6 grams per milliliter for the density. Because what? Why is that? Why would you have to have more water in your column than mercury? Ooh, a logic question. Uh-oh. I'm making you logic things. Use your brain. Exercise it a little bit. Okay, folks, go ahead and get that answer in. I'm going to move forward. Okay, I am moving forward. So, is mercury less dense than water or more dense than water? Mercury is more dense than water. You got it. And so the issue is that water just doesn't have the weight to offset that pressure, right? Okay. So for example, if you were to make a squirt gun with shot mercury, you'd only be able to shoot little beads of mercury, right? On the other hand, you can shoot large streams of water, right? Yeah. And again, that's just due to the weight, how much weight you have to move. Okay, let's talk about some relationships. So Boyle's law, does anybody know the difference between a law and theory anymore? Yeah, so a law is something that we observe all the time. It's continuously confirmed for us. A theory is something we cannot observe all the time, and so we only have a limited set of data that tries to disprove it. Okay? And so in this case, we're observing this all the time with every breath we're taking. Okay? So Boyle's law states that the pressure of a gas is inversely related to the volume as we hold the temperature constant. And you can actually see this if you take a water bottle that's closed and it's mostly full of gas. If you press down on it, its resistance increases against you, doesn't it? And it pressurizes it, doesn't it? And that's what you're seeing. You're shrinking the volume, that's increasing the pressure, isn't it? Okay, we can mathematically relate this as P1 times V1. So the pressure times the volume of one state equals the pressure times the volume of the other state. And that makes those inversely related, pressure and volume of a state. Okay, again, this would be a restatement just with the temperature being held constant. If you were to change the temperature, that would also affect pressure and volume. Yeah, I'll post the changed lecture. Yeah, I've taken out slides and put the deals in. If you email me to remind me, it'll help. Yeah, because unfortunately, by the time I get back, I'll be teaching like 4 hours straight. Okay, so note that if we have a given system, it's always going to end up with the same atmospheres times liters. Okay, so if we have a system and it was 8 atmospheres and 2 liters, if we then go to 4 atmospheres, it has to be 4 liters. The same atmospheres times liters number. Okay. All right, so let's look at proof of this that you can easily demonstrate right now. You've been demonstrating all class, right? All right, so during inhalation, what happens to your lungs? Everybody do it. Lungs are expanding, right? Okay. What's happening to the pressure in those lungs as we hold that inhalation? The pressure has increased, hasn't it? We have to fight against it to keep it in. We've increased our pressure. This is why we can use it to do things like speak, like I am right now. I am decreasing my pressure. The air flows towards the lower pressure in the lungs, and that's what we do when you exhale. What happens to our volume then? Yeah, we decrease, don't we? All right, so exhalation, lung volume decreases. Pressure within the lungs is going to decrease. If we had the same amount of air in it, we would end up increasing our pressure. let me restate this. Okay, so if we were to hold our mouth closed, hold our nose closed, okay, what would happen to that air in our lungs? We take it in, and there's a lot of pressure buildup, right? As our lungs try to close down. Our diaphragm tries to squeeze back in, right? And so if you're trying to, say, play an instrument, what do you do to play the instrument? You exhale, right? Yeah. Why are you exhaling to play that instrument? You're squeezing that lung to be a lower volume, right? The pressure of that gas increases, that causes it to expel at a higher pressure or more energetically, right? Okay. Okay. Is that making sense so far? Fantastic. Why do your lungs fill when you go ahead and increase that volume? What happens when you make a vacuum? Something tries to fill the vacuum. So when you increase the volume, you decrease that pressure below the atmospheric pressure. The atmosphere tries to fill the vacuum. Okay? That's why the air comes in. Okay, so let's look at Charles' law. This is going to be the Kelvin temperature of a gas is directly related to the volume. So as you increase the temperature of a container, what happens to that gas? It expands, right? And you've all experienced this probably with balloons. The other place you might have experienced it is if you have like, anybody ever had a container of like paint thinner and you're working outdoors and then you put it in the garage and it collapses, right? Yeah. And that's because you were high temperature, you brought it into a low temperature environment and the gas collapses, lower pressure, the can collapsed. Okay. All right. Same thing, you can demonstrate mostly the same thing with a balloon as well. Okay. Okay, so volume and temperature are directly proportional. This is the mathematical way to represent that. V1 over T1 equals V2 over T2. So as you increase volume, you have to do what to the temperature? Increase it. You got it. This is also how the next one is actually how a fridge works right here. Has anybody, no, we've just established this, haven't we? Since I've talked to you, has anybody went behind an air conditioner or fridge to the other side of it? What the heck?
I can't get behind my fridge.
How about the air conditioner? There's the air conditioner on the outside, and
Yeah, I was gonna say.
this is just sad. We need more curiosity.
My fridge is against the wall.
Does anybody know the saying for the cat?
Curiosity kills it.
Killed the cat? Is that the full saying?
Yes.
It is not. Satisfaction brought it back. Yep. Yeah, it's actually has a completely different meaning. I know. People shortened it and changed the meaning to it, which is really sad. All right, so this is a Gay-Lussac's law. This one is going to be as you increase the temperature, you increase the pressure. You've all experienced this. I can't use the example of your compressors on your fridge or your air conditioning, apparently. Has everybody used a tea kettle?
No.
No? Has everybody seen a tea kettle?
Not in person.
Steam engine? No? People haven't seen a steam engine? How about what? Yeah. Yeah, steam engine on a train works. Yeah, if you've seen a train, then you got it. Yeah, so they're throwing in coal to the train, right? They're heating a boiler. Everybody's comfortable with that so far, right? And so why they're heating the boiler is that they're trying to... Why am I going backwards in time and technology? What the heck? Like all the modern examples, no. The 1800 example, okay. But okay, anyways. So they're increasing the temperature of the boiler, the water, right? And that increases the pressure. They can use that pressure to drive the steam engine, i.e., that mechanism that moves the wheels, right? Okay. Everybody's good with that? Fantastic. Okay. Am I going to have to do like 1850s references? Okay. Okay. Okay, that will work. This is in Kelvin, by the way, because we can set this at a absolute scale. Do note, however, what would happen if we get to 0 Kelvin here? Yeah, we would divide by 0 and math would blow up. Okay. Okay. So we can combine all of these laws. We have Boyle's law, Charles' law, and Gay-Lussac's law. Notice that each of them held one condition constant, right? So we take all these laws, we combine them together. This gives you what's called the combined gas law. Now, you guys may have heard of a gas law before. It may have been the combined gas law, which is this one right here, but it also may have been the ideal gas law. Okay? Okay, so the combined gas law, the pressure volume divided by temperature of one state equals the pressure volume divided by temperature of the other state. Okay? This works very, very well for a large number of systems because this is a law. Yeah, this will always be true. Right? If it's not true, guess what it is not? A law. Isn't a law anymore. It would be a theory then, because it has failings. Okay, and so again, this is just the summary of that. So a gas has a volume of 675 milliliters at 35 degrees Celsius, 646 mmHg pressure. What is the volume in milliliters of the gas at negative 95 degrees Celsius and a pressure of 802 mmHg? In this case, the N, the number of moles, the amount of gas is going to be constant because we haven't done anything with that yet. We don't know how to include that yet. Okay? Okay, now, there's only one place here that the units really particularly matter. Anybody know where the units matter and we have to do a unit conversion? Yeah, the Celsius. That one needs to go in Kelvin. Every other unit in this would all be multiplications to convert the units. And then that means that we don't have to convert them because they would just cancel out every conversion. Okay? As long as we're the same units on both sides for everything but temperature, we're okay. Temperature is unique because that has to be in Kelvin. And again, that's because we have to add a number to make it in Kelvin, right? So how do we get Kelvin plus 273, right? All right, so we take the 35 plus 273, that gives us 308 Kelvin for the temperature 1, which is right up there. The next thing we do is we take the second temperature, temperature 2, negative 95, and we're going to add 273 to that. That's going to give us 178 Kelvin. Everybody good with that so far? All right, fantastic. The next thing we need to do is we have a set of volume, pressure, temperature, and then on the other side we have a temperature and pressure, right? So we're going to need to use that combined gas law to get this. All right, so the next thing we're going to do is we're going to take the combined gas law. I think it's probably easier to go ahead and solve the combined gas law to leave volume on one side. Most people will probably find that easier. And so I go ahead and take the combined gas law. I divide over the P2, and the T2 gets multiplied over. And that's what I'm getting right here. So I've just solved it. So the combined gas law has V2 on one side. It's the only term I don't have from what I was given, right? All right, so the next thing I need to do is I need to go ahead and put in my values, okay? So my volume, V1, this one here is V1, right? This here then, in Kelvin, has to be my T1. And this has to be my P1, my pressure. Okay. And so I'm going to take that, 675 milliliters. I'm going to plug that in for my V1 here. Over here, the next part, I'm going to take my pressure 1, the pressure that corresponds to that volume. I'm going to plug that in. I'm then going to divide it by my pressure for the other set of conditions, the second set of conditions right here. So that's going to be the 646 divided by 802. Okay. The next thing I'm going to do is I'm going to take my numbers for temperature that I've converted to Kelvin. I'm then going to take that, and my T2 goes on top, my T1 goes on bottom.
Can you explain how you do your I don't understand.
Oh, okay. So what we do here is we have a P1, you can see that one, right? Okay. So we have the P1 V1 over T1. And then on the other side, we have P2 V2 over T2.
So it's possible to just plug in all of your numbers for like the variables in P1, V1, and then just solve for X, right? Like,
Yes,
okay.
you can. Yeah. Yeah, if you want to plug in the numbers first, that's fine. For solving it on a screen like this, that becomes very difficult because then I'd have to move parenthesis values, right? But yes, you can do that. That's fine. If you had put this in, then you'd put P2 in there. And here would be that T2, which is the 178 Kelvin. Okay, let me make a new slide real quick. I need some space, so I'm going to clear this, and I can show you how to solve for this as well. Okay. All right, so how you solve for this is right here we have P1 V1 over T1. This equals P2 V2 over T2. We want V2 by ourselves, right? So we're going to go ahead and move the T2 over, the P2 over. Now when we try to get rid of things, what do we have to do? We have to multiply both sides, right? So I multiply T2 on both sides. Everybody good with that so far? Okay, that will cancel here. And that would leave me with T2 times P1 V1 over T1. Okay. Okay, that's going to be equal then. I'm going to put my equals over here just to make my life a little easier, okay? Okay, so I'm left with, still on the other side, the P2 and the V2. Okay, we good with that so far? Fantastic. Okay, and so the next thing we need to do is get rid of the P2 from the left side now, right? So I go ahead and divide by P2, and I divide the other side by P2. Now, when I divide by P2, there's two ways I can write it. I can either divide here by P2 like so. Okay? Or I could also have written it as times 1 over P2. Both mean the same thing. Okay. Okay. And so I'm going to go ahead and rewrite that. I have now P2's over here canceled. So I'm left with V2 equals, and then that's going to be T2. Were you more comfortable with the T2 over P2? Or 1 over P2? And it just being left on its own? Anybody more comfortable either way? Okay. Okay. Did you get lost here at all?
I got that part, I think. But
You're okay with that part so far? Okay. Okay. This is over P2. This is times P1 V1 over T1. Okay. I can rearrange that then so that I have each term, the pressures with the pressure, the temperature with the temperature. Okay? And that's because the order of operations for multiplication, they're all the same order, right? So I can go ahead and rearrange that to be any order I want. Okay? So I'm going to go ahead and do that. V2 equals T2. Huh? That's true. I can use the whiteboard if you want. Yeah.
There's a marker on that side.
Yeah, I have to go over there to get my marker. And I have a cord that I have to extend. Okay. Sure, we can use the whiteboard. Okay, did you want me to start from the beginning?
No, you're good. I just can't read what you're writing when you're writing it over like other letters.
Okay. So our V2 had been equal to, can you guys tell me the equation real quick? That was that?
Oh, no, I don't know where. T2 over T1.
Okay, everybody, let's just start at this V2, T2 over to P2, and we'll start there, okay? And I'll rearrange on this board here. Okay, and so that was P1 over V1 over T1. Okay. Everybody with that so far? Okay, all I did before was V2, P2, T2 equals P1, V1 over T1. What I did then was I said, well, I have to multiply P2, P2, so these things cancel out. I have to do the same thing to both sides, and so I do the exact same thing to the other side, like so. Okay. All right. So the next thing I'm going to do is you can simplify this a little bit to, again, see your relationships more clearly by grouping up each of the pressures and each of the temperatures and the volume. So my volume, I'm going to put it first. It's on top. It's still on top, right? Okay. And so then I'm going to take my next relationship. I believe I did pressures in these. Yeah. And so my pressure 1, see how it's on top here? I have to keep that on top, right? My pressure 2 is on bottom of this nest. And so I go like that. And then I go ahead and do the same thing with my temperatures. T2 on top, T1 on bottom. Okay? And that's all I did. If you get comfortable with comfortable enough with the math, you don't actually have to do this in 2 steps. Yeah. This could have been done in 1 step. Okay. Okay, everybody got that part? Fantastic. If you're not comfortable with the math and you want to lean on your calculator a lot, you can plug the numbers in, simplify the numbers in your calculator. It will work. Just remember, you have to be very careful about your order of operations and parentheses, okay? Mm-hmm. Yeah, I haven't uploaded this version. Yeah, it's still the old 8.1, I believe. Oh, okay. I'll upload this version. Go ahead and email me to remind me, though, because I'm going to have a very long day after this. Yeah. Yeah. Like, I will not get a chance to do anything until 4:30 tonight. I'll be in front of classes the entire rest of the time. Okay. So, all right. So we just plug these numbers in. We go and solve them with our calculator, right?
Yes.
Okay. We get 314 milliliters. Please appreciate and notice that we don't have to do anything with these units because they're all the same units and they all cancel out, right? Okay. So now you guys do it.
No. Don't make me.
Okay. So a sample of helium gas has a volume of 0.180 liters, pressure of 0.800 atmospheres, and a temperature of 29 degrees Celsius. At what temperature in degrees Celsius will the helium have a volume of 90 milliliters and a pressure of 3.2 atmospheres? And again, the amount of gas in remains constant because we haven't done anything with that yet. Okay. Yeah, okay. Okay. Okay, try your best on it. Give it a good, honest workup, or a collegiate try, as it were.
Oh my god. So I actually got 58,000. I think that's the answer. No, I got that. Oh, okay.
Okay. Please look at the units. Be careful about the units. There's parts of this problem I did not give you the same units for everything. And I gave you things like degrees Celsius where you need Kelvin, right?
See, I got something that wasn't an answer to this either. So.
I got 58,000.
Okay.
I think that's right.
Now I'll tell you, if that was 58,000, what we could get by doing something like this, the energy crisis wouldn't be a crisis that we would like, it'd be, fusion would have been a solved problem. Also, you would have been able to set off a fusion reaction with like taking a balloon and going pop.
You have to convert it to Kelvin first, or can we just keep it in?
Yes. Yep. You always have to go to Kelvin first.
Oh, that's true.
Yeah, that's why I was mentioning the temperature is the only one that you have to convert. You always have to convert it to Kelvin.
Yes.
Because I need you to learn to convert it to Kelvin.
It needs to be in there, give it to us.
I guess.
Oh, I just figured it out.
Okay. Just don't do the other parts of the Eureka. The school would look down on that one. I'm pretty sure. You can help people around you. Yeah, and whenever we're doing these, please do. If you think you figured it out, help people around you. Like you learn it better by interacting with each other.
Yes.
Okay. Is anybody still having valuable time that they're putting into this? Okay. Fair enough.
Hey, so I got 50 off.
So I got negative
Okay.
5.
But that's probably not honest. I'm just glad it was August.
Oops.
Wait, when you convert
Okay, folks. So go ahead and wrap up. I'll give you another minute, and then we'll move forward.
No one can convert it to milliliters.
Yeah, you can convert to milliliters or liters in this problem, by the way. But you have to have the same for both.
I don't know what she did.
I do wrong.
I don't know what you did.
I got here.
I remember you doing this in the closet.
Okay, folks. Unless anybody's making valuable way forward, I'm going to go ahead and go on. All right.
Hey. Oh.
Wow.
I think it's right. I guess.
That is correct. That is correct. Yes, indeed. Okay, so what's the first thing I have to do in this problem, by the way? Yeah, I need to convert everything into units that I can work in, right? And so one of the things I need to convert is degrees Celsius. That has to go into Kelvin, right? So 29 plus 273, 302 Kelvin. Okay. The other thing I need to do is I have a number here that is in liters. Over here I have milliliters, don't I? Okay. So the number of liters is probably the easiest to convert into milliliters because most people like to work in whole numbers, right? But you can go either way. It doesn't really matter. So as long as they're both the same. So what I'm going to do here is 0.180 liters. That would be the same as 180 milliliters. Okay. Everybody okay with that part so far?
Yes.
Fantastic. Okay, so the next part I'm going to do here is I have atmospheres versus atmospheres. I'm good for that, aren't I?
Yes.
Fantastic. So now I need my formula. Mm-hmm. You can just use gas law. Oh, did you use the ideal gas law?
Times 0.8.
Because they were both going down. I think they were going up.
Oh, yes. Yes, yeah. Be a little bit careful of that, just because, yeah. But yes, definitely. In a multiple choice question, you could always just use general trends. Yeah. Yeah. I don't care. Yeah. Yeah. No, if you can do it, you can do it. Okay.
Wait, I'm
All right. So in this, I'm going to go ahead and solve it for T2 to be on its own. So T2 equals T1 times P2 over P1 times V2 over V1. I'm then going to plug in my values. So T1 is 302 Kelvin. Then I have my atmospheres, my pressures. The 3.2 goes on top here. The 0.8 goes on bottom. Then next, I'm going to take my volumes. My 90 goes on top. My 180 goes on bottom. Anybody have any questions so far? Okay.
Instead of doing it that way, could you show us how to do it with just like plugging in the numbers?
Sure. Sure, we can do that. So, which one's going to be my one? The first set? This stuff?
Yeah.
Okay. Okay, sounds good. Okay, so I take my P. That is 0.8 atmospheres, right? That's my P1, my pressure for the state one. I can't hear you guys over each other.
We were asking what it said.
Oh, okay. 0.8. Sure, we can go on the board if you guys are having difficulty reading. Okay, so again, I have my P1 V1 equals T1 over T1, right? I'm just going to fill that in. So my pressure is the atmosphere's number. So 0.800 atm.
Yes.
Okay, that was my P1, right? All right, so my next one is going to be my V1, right?
180 milliliters.
180 milliliters, you got it. Okay, and that's my V1, isn't it? Okay, what's my bottom?
302.
302, that sounds correct. That is my T1. Okay, and then I go over to the other side, I fill that one in. So what's my P2?
3.2
Okay, very good,
times 90 milliliters
very good.
over X.
I'm going to keep it as T2, but yeah, that's already a variable, but you can replace it with an X if you want. Okay, so I imagine you would all like to simplify. Simplification is probably the easiest way here. So the first thing I'm going to simplify is this. I multiply these together, and what do I get?
280.
Okay, 200 and, what did you say?
280.
280? That sounds about right.
That's fine.
Okay. Alright, and that stays T over T2. Then this is going to equal, okay, so I'm going to simplify this one. 0.8 times a 180.
144.
What was that?
144.
144? Can you guys even still see that? Okay. And that would have atmospheres, milliliters. All right, so the next thing I'm going to do is I'm going to take the 144 divided by 302. And what do I get for that? 0.4768.
Yep.
Okay, thank you. ATM times ml over Kelvin. Okay, so what's the next step I need to do?
You need to get T2 by itself, so if we move it to the other side, like multiply it on both sides.
You got it. Times T2 to both sides, right? Okay.
This is not-
T2 then cancels on this side. On the-
And you divide the 0.4 by, like, 288 divided by.
You got it. 0.468. And this one's divided by 0.4768. So I multiply T2 over, then I divide by this number here on both sides.
And then that's your answer.
That's my answer. All right, you all have a wonderful day. I'll see you next week. What's happening next week again? Exam, right? Be ready for the exam. This is not on this exam. This will be on the next exam.